Hello everybody, welcome back to the ASUS RG YouTube channel. This is JJ once again, and we've got something pretty cool for you this time around. We've done a couple of other videos showcasing auto overclocking technologies on our ASUS X79 series of motherboards, but today what we're going to be focusing in on is actually how to manually overclock your system, as well as kind of taking in some of the considerations relative to the platform, the CPU overall architecture, as well as kind of some of the requirements you're going to need to have when you're overclocking X79 and Sandy Bridge G and our motherboards. So let's go ahead and jump into it from a little bit of a high level initially. So first and foremost, you want to make sure that prior to any overclocking, you've gone ahead and completed pretty much everything you need to get done first on your system. So this means that pretty much get everything installed inside your chassis, make sure that everything works correctly, install the operating system, even run a couple of general benchmarks, maybe even a game or two, make sure the system is operating exactly as you need it to be. The main reason is that you want to go ahead and have a baseline. You want to know that the system is working reliably without any issues, everything's gone through overall without any type of parameter problems in terms of whether the system might be crashing, whether there might be an anomaly in terms of your temperatures, who knows, a number of different variables. But overall, just make sure that the system is working accordingly. I also strongly advise that when you're overclock in the exact environment that you're actually going to be in. So take for example, we're not actually going to be overclocking on a test bed. The main reason being is that while a test bed can be a great platform to give you some relative insight in terms of what's capable, it's not necessarily always going to be realistic of what you're going to be able to readily accomplish in terms of actually your 24/7 defined parameters. So as you can see here, we've actually gone ahead and set up a system. So it's pretty much all completed. I've got my operating system installed, I've run benchmarks on it, I've done all kinds of different things. This is actually the same exact system that we've utilized for many of the other videos that we have here for the ASUS X79 launch. So this system's already pretty much burned in, and this is what we're going to be using as our baseline. So keeping that important key point in mind, we're now going to go ahead and move over to some of the considerations you're going to want to make when working with the platform. So I'm going to go ahead and grab over here one of our actual motherboards. So here we've got our P9 X79 motherboard, our Pro. So this is up from our mainstream channel series of motherboards. It's a fantastic board, features all of our kind of key technologies. Really the ones that we're going to be focusing in on today are going to be the actual functionality. It's offered by our TPU integration, which is part of our dual intelligent processors 3 design, and our actually overall Digi Plus VRM and Digi power control system. And that's essentially our digital controllers for both the VRM and for the DRAM. This is going to be key in terms of giving us a lot of flexibility at how to define the parameters that we're looking for. Now, what you can see when you're first looking at an X79 board is that first and foremost, the socket's quite a bit larger. Of course, we have memory banks onto the right side as well as to the left side of the board. We can also see that we have a considerably more packed VRM area. So this portion right here is the actual VRM heatsink. This is pretty much where all the key power delivery componentry is underneath. So things like your MOSFETs, your drivers, your chokes, they're all pretty much underneath this heatsink assembly. And this is going to be an area that's going to be critical in terms of ensuring solid, consistent airflow. Now, for moderate level overclocking, such as like when you use the TPU switch, you flip it up to like 4.2, 4.3 gigahertz, you're generally not going to need to ensure that this area is that adequately well cooled. Even in some situations with no overall airflow, you could still assure strong performance, no overall throttling. Throttling would be that when potentially either the CPU or the VRM gets too hot, the CPU itself can actually go ahead and downclock, or it can throttle downwards. Ideally, of course, because this reduces performance, it's not something that you'd like to have. So keep in mind that we want to have consistent airflow, not only to the foreground of the actual heatsink VRM, but also to the actual backplane. This area actually has portions of the actual VRM underneath this as well, so we want to try to keep that cool if possible. Now we can see here on this board we've got a little bit more elaborate heat pipe solution, which extends out to a secondary heatsink. So any additional airflow that we can either directly provide to this area as well as that we can exhaust out to this area is key. Now, overall, my initial recommendation in terms of cooling options is going to be actually going with a closed loop solution. As you can actually see in the system here behind us, we actually have a Corsair H60. So this is a great option. For one, as we can see, is that it keeps the overall the VRM area and the CPU socket area clean. It's not compacted with a lot of items. And another critical item is that the majority of fans that are on the market when you're talking about a standard air cooling solution are generally going to exhaust hot air, and that hot air is generally going to migrate right over to this actual DRAM area. Now the negative thing about that is that as this hot air builds up directly over these modules, as well as actually over this portion of the board, this can cause potential instability because the DRAM itself could easily start exceeding 60, 70, maybe even 80 C. So the operational temperature can become quite high, and that can lead to potential memory instability parameters, as well as overall just instability relative to the board as this area is getting a large amount of heat that's consistently being put onto it. Now, of course, a back 120mm fan or even 140mm fan could help to exhaust that and keep a more equalized temperature, as well as a more consistent level of airflow to draw that heat outwards. But a closed loop solution, I feel, is going to be ideal. So we can actually see here, we've got a couple of different options. So here we've got the Corsair H60, which actually we've outfitted here in our Corsair Carbide 400R chassis. And this is a great option for users that are generally going to be looking at, I'd say, 4.4 to about 4.6 gigahertz. Now, at 4.6 gigahertz, if you're starting to run synthetic stress test applications like Prime 95, limpet-based applications, the potential wattage, as well as the corresponding voltage and frequency that's present, could start to put out an actual TEP that could be very difficult for the unit to be able to take care of in an actual quiet fashion. Not that the actual cooling performance still wouldn't be quite robust, but potentially it's going to be a little bit louder than you want. Now, there are different options to go ahead and alleviate this if you were to maybe transpose and go to a larger fan from the standard 120mm, maybe 140mm. Could be an option, but you'd have to do one of like the 120mm fans, 140mm fans that have 120mm screw holes, so that you could go ahead and outfit that into a normal chassis. But this is going to be a great solution for the majority of users, because the majority of CPUs pretty much across the board are able to comfortably hit 4.5 to 4.6 gigahertz. And keep in mind that the relative overall temperatures under normal real-world usage, such as actually when you're playing a game like Rage or Crisis or Battlefield, Witcher, whatever it might be, or general web browsing, application usage, Photoshop, things like that, you're generally not going to be looking at consistent high-level loads across all cores. So the temperature is going to be significantly less than the stress points that are induced by those synthetic applications that we noted earlier. So this could actually still be a great solution for that 4.6 gigahertz frequency. Now, stepping over this guy, and if you want to go ahead and extend overclocking performance even further, we've got something like the Corsair H80. This unit's awesome, and it really helps to go ahead and give us a bit more robust cooling performance, especially as we start to go ahead and go past the 4.6 gigahertz marker. So this is going to really be targeted, I'd say, at users at between 4.6 and potentially up to 4.8. And here, of course, you have two fans to be able to help improve the overall heat dissipation ability, as well as a significantly larger radiator. So this is going to be a great option for those users that are considering that. And all the initial notes that I made in reference to realistic temperatures, as well as the temperatures that can be dissipated actively in a quiet fashion by this unit, still hold true in terms of what we noted before. But this being that this unit has better heat dissipation abilities, this is still going to go ahead and be able, and even with those higher level synthetics, be able to provide you solid level cooling. With that in mind, once you start to get to 4.8, some of the corresponding voltage levels or the VID tables that are required could become quite aggressive, and the corresponding heat that has to be dissipated could easily be in excess of 180 to 190 watts, sometimes even potentially more. At that point, this unit is still going to be able to get the job done, but you're going to start eking closer and closer to what's referred to as the TCC point for the actual CPU, where it potentially could shut down, could reach a thermal junction point. So this is Corsair H80. For the guys that really want to push the envelope, this is probably my favorite cooler here in terms of what we've done a lot of internal testing with, and this is the H100. This actually unit works fantastic also within this chassis, because you can go ahead and mount the H100 directly on top here, and in the ideal situation you can actually have the actual fans set to downward fire. As we discussed before, one of the key aspects is in keeping this overall VRS assembly cool. And actually the way that we have our actual Carbide chassis set up is that we have a 120mm fan, another 120mm fan, another 120mm, and another 120mm here. So we have four that are set up here. And these are actually 4-pin fans by Cooler Master, their Excalibur series. They're fantastic because with that 4-pin it gives us the flexibility at setting manual fan controls set up specifically for their position and what they need to do in terms of the air cooling and to the relative acoustic levels that we want to have them under load. Now we've gone ahead and set these fans up so that they actually blow downward, so that actually gives us airflow crossing directly down our DIMMs. And that's going to be key because especially as we start to really stress the memory, and if you're using a high amount of it, the memory can get quite hot. And this helps us to ensure better overall long-term reliability and ensure the lifespan of the actual components that we're working with. In addition to that, that downflow of air is also coming directly across the actual heatsink assembly. And as we can see, we've actually finned the assembly to be able to take advantage of this. So we're getting that cool air that's not only coming down across this VRM heatsink, but it's also coming across the actual backplane. So this really kind of gives us the perfect storm of giving us ideal cooling with this unit. So not only do you have the very large, massive radiator here to go ahead and assist in the actual dissipation of the heat from the CPU, but you got the fans here set up, and then from there you can have an exhaust out in terms of another 120mm or 140mm fan set up there. So overall, really giving you great performance. And this cooler, of course, depending on the relative fan settings, is really going to be able to offer you 4.8 and plus in terms of the actual frequencies that it can handle under load. So that gives us a little bit of an overall perspective relating to some of the recommendations that we're going to keep in mind when we talk about cooling a system, as well as the actual chassis configuration. So now that we've outlined, one, the actual considerations that we have in terms of adequate airflow to the motherboard, two, the type of actually airflow configuration that we'd like to ideally have within a chassis, we also want to call out actually utilizing quality componentry. So one, we've got a very high quality PSU present in the system. So we're actually tapping Corsair's AX series. The key reason why we've tapped them is because these PSUs are gold rated, they're 90% efficient. So that means that we're getting a very, very high level of the actual wattage that's been defined for the unit actually being usable. And it also helps to actually provide us a significantly quieter system. So we get really clean power delivery, consistent power delivery even under load, and varying levels of load, which is also key. And we also have qualification for the newest standards in terms of like C6 or C7, which are special low power states that are actually now supported under the Sandy Bridge E architecture. Now, one of the other key parameters to keep in mind is that with Sandy Bridge E, when you're heavily overclocking the platform, the potential wattage in terms of what can be drawn from the CPU alone at corresponding frequencies like 4.7 to even 4.9 gigahertz can be between 180 to 215 watts in terms of draw. This is an exceedingly high level, so you really need to ensure they have a quality PSU. Secondary to that, to the amperage that coincides to that, which is generally listed on your PSU, can easily be in excess of 25 to 30 amps. So once again, you need a quality PSU that's comfortably going to be spec'd at that margin. So you'd always want to try to overshoot it a little bit to make sure that you're not going to run into any issues over the actual lifespan of the product, because sometimes over time, the actual parameters of operation are going to drop down a little bit due to just normal operational usage. So this is a key aspect to consider. So we've got a quality power supply here, we've got a great closed loop water cooling solution, we've got our airflow set up, we've got some solid memory that we're using here. We've tapped Corsair's DDR3 1600 Vengeance modules. We're not necessarily going to really aggressively be pushing the memory divider, and the main reason being is that with the Sandy Bridge E CPUs, there tends to actually be a fairly strong variance in terms of the quality of the integrated memory controller. While the Intel specification definitely supports higher memory dividers than 1600 for Sandy Bridge E, there's always going to be the variance at actually what's the reality at the frequency you can run at and with how many DIMMs. Now we've done very lengthy qualification and tuning to be able to ensure that our boards can hit 1600, 1866, 2133, even 2400. On our RG boards, we've done internal testing, even pushing past 2700 in full 8 DIMM, 32 gigabyte configurations. With 64 gigabytes, we've done in excess of 2000 in terms of the frequency. So definitely we're not limited by our actual trace layout, our UEFI tuning, and our power delivery systems on our board, but you're going to definitely be restricted per the variance of the CPU. With 1600 definitely offering you a huge amount of bandwidth, especially with the refined memory controller that's on Sandy Bridge E, most situations it's going to be able to get the job done and give you an outstanding value as well for the pricing. In most situations, you're going to be looking at 16 gigabytes, approximately about 100 bucks. As you start to go up, it's going to get considerably more costly to be able to get to those higher frequencies, where there is definitely going to be a return on the value, especially if you start to consider things like RAM caches or RAM disks. But overall, in terms of gaming performance potential, 1600 really kind of gives us that sweet spot in terms of operational efficiency. So that overall kind of gives us a little bit of an outline relative to some of the specifics that we have here set up in our system. The next thing that we're actually going to do is we're going to jump into the actual UEFI and actually start to take a look at some of the parameters that are available to us now that we have Sandy Bridge E, and some of the new options that have been introduced for overclocking that are specific to Sandy Bridge E. Now, once again, I would like to reaffirm that there is going to be variance, or what's referred to as CPU margin, from one CPU to another CPU. So that means some CPUs are going to comfortably be able to get up to 4.6, others are going to be able to get to 4.8, and others might even be able to reach 5 gigahertz. Now keep in mind that the relative voltages for these frequencies can significantly vary. We've seen some 4.8 CPUs that are very solid in terms of their quality be able to actually operate under full load with as little as voltages about 1.405 to 1.415 in terms of the actual VID, while other CPUs could actually have that same voltage table but for a significantly lower frequency, like 4.6. So keep in mind, margin does vary. But what we are going to do is show you some tips and tricks to help you kind of quantify and see where you might be at in terms of the quality of your actual CPU. So let's go ahead and now actually jump into the UEFI and take a look at some of the new options that are available. Now, as we go ahead and we have our system actually reboot here, we want to make another general note is I usually always recommend have like a little piece of paper and a pen so that if you want to go ahead and make some quick notes regarding certain settings or certain items that are important to the actual overclocking experience as you're running through it, you've got something to be able to notate that down. So that's key. 2, always make sure to have your handy water bottle here. When you're overclocking, sometimes the process can take you a bit of time. Kind of go through a lot of different parameters, and it's always nice to just have, cool sip of water and be good to go and go ahead and get cracking back at it. So I'm going to go ahead and take a quick drink of water as we get here into the UEFI and get ready to start going over some of the more advanced options that are now available under Sandy Bridge E. All right, put my water here to the side. Let's go ahead and now actually jump into the UEFI. So we're going to jump straight into advanced mode because we're going to be focusing on advanced manual level overclocking. So, most important section within the UEFI BIOS for X79 Sandy Bridge E is going to be AI Tweaker. With AI Tweaker, this pretty much contains all the key parameters that we're going to need for defining all the key aspects for overclocking the Sandy Bridge E platform. Okay, so first option that we're going to see here is going to be our AI Overclock Tuner. And what we're interested in doing is setting this to manual. Manual is going to go ahead and open this up to be able to go ahead and have the most ranges of operation and definable parameters, such as now BCLK, CPU, strap, and the turbo ratio. Now for the BCLK, for those of you aren't aware of the limitations that were present on the 1155 platform, is an actual replacement for the previous front-side bus architecture. The disadvantage of the BCLK is that the way that the actual architecture ties in other buses is that it's a bus that doesn't generally like to be moved a lot. So generally your range of operation, or in terms of the range of definable operation for this, is going to be fairly small. So by default right now we've got it set to 100, and operational maybe adjustment could be up to 103, 105. This can vary slightly on the quality of the CPU. Now there are certain more advanced options that we'll actually have covered in our ROG overclocking, where we have some special hardware that can extend the BCLK overclocking parameter. But for the most part, I generally do not advise that the BCLK be modified from its stock operating value of 100. So we're not actually going to go ahead and touch that. Now one of the new options that we do have though is what's referred to as the CPU strap. Intel has actually done some pretty awesome stuff actually with this strap. Essentially what they've done is they have an external clock generator that decouples and allows us to go ahead and essentially make BCLK adjustments, but without readily affecting other buses. So essentially what you do have is you have these strap values of 100, 125, 166, and 250. These themselves will actually make an adjustment to your primary target frequency. So if we set this to 125, we can actually see that now it actually would take our corresponding frequency to 4.5 in terms of 4.5 gigahertz. Okay, and if we were then go ahead and set it to 166, it would take us to a different strap. And there's modifications that are being made in terms of the actual turbo ratio, because if we go ahead and define the turbo ratio, we'll also make corresponding adjustments to that CPU frequency, because it's going to be the strap times the multiplier in terms of your maximum frequency that's going to be achieved. Now, some considerations to take into the strap is that All CPUs will work, of course, at 100, and pretty much the majority of all CPUs that we've tested do also operate at 125. But we have found very few CPUs that can generally hold the 166 megahertz strap, even though the frequency that it actually defines is relatively within the same operational frequency potential of most CPUs. So do be aware of that. So because of these parameters, I generally am not recommending that the strap also be adjusted. In some situations though, where the strap can become useful is actually in adjusting your memory divider. Now if we take a look, and once again we just go ahead and reload our defaults, go back to manual, we can take a look at actually some of our options for the memory frequency. We have 800, 1066, 1333, 1600, 1866, and 2133. Now one divider that we don't see is 2000, which was previously a more common memory divider. Now the benefit that we have with the strap is that we could go ahead and define, let's say 125, and actually now have a new set of memory dividers. Now this gives us a little bit more flexibility that if you have memory modules that have some leeway possibly past 1866, but potentially not up to 2133 and closer to 2000, you could go ahead and have that memory divider present. Of course, the other option you could do with that is that after actually successfully overclocking your turbo multiplier to the frequency that you want, you could go ahead and adjust your BCAK value on top of a defined on top of a memory divider to go ahead and also achieve that kind of in-between memory divider. So as an example of that is if we were to go back and we were to reset manual, we could go ahead and select 1600, for example, and if we were to slightly adjust our BCLK maybe to like 103, we could actually see that we get 1648. So you can see that there are a couple of different options in terms of how to tweak and tune your system. But generally, I do not advise taking liberties with DRAM overclocking. The main reason being is that DRAM can be very sensitive on subtiming levels. And especially with 4 gigabyte DIMMs, 4 gigabyte DIMMs tend to not have as much leeway in terms of advanced subtimings, and in terms of being able to push these higher frequencies. Now, the Vengeance modules that we worked with definitely sometimes have headroom in terms of being able to extend past their baseline operating parameters, but for the overall lifespan and the overall performance that's already offered, I recommend running their nominal values. So this kit, take for instance, would be 1600 C9 at 1.5 volts. That's pretty much what I want to stay at, and my focus will be on the CPU frequency. So keep that in mind. Independent of that, lastly we have what's referred to as our turbo ratio. With our turbo ratio, this is essentially going to be the key value that lets us increase the actual CPU clock frequency, so push up the actual gigahertz. Now we have two options. We have one that allows you to actually make real-time adjustments after you define these within the operating system, and we'll touch on that in a little bit later. The other option is going to be per core. Per core is not generally used by a lot of the overclocking community, but it's actually an amazing option at being able to help you extend the operational frequency of your CPU, especially when your CPU tends to have a limitation at certain multipliers. Now, an example of that might be is that maybe your quality of your CPU doesn't allow you to run 48 across all cores due to the relative heat and voltage and a lot of different variables, or it could just be that it's a weaker multiplier in your CPU. So what you could actually do is potentially maybe say, okay, I'm going to go ahead and for 5 and 6 cores, I'm going to actually run this at 46, and then at 3 to 4 cores, run this at 47, and then at 1 to 2 cores, run that at 48. And the corresponding wattage in VID is actually going to be far less for this configuration than it would be if I was attempting to actually consistently run 48 across all tables. Now, of course, ideally, if we could run all fixed at a 48, that would be fantastic. But there's always considerations to take into mind so that when you're actually defining these overclocking parameters, that you don't have any control over relative to the overall quality of your CPU, to the temperatures that you have, to the voltages required, and a lot of other parameters. So per core is definitely an interesting option that you always kind of want to be conscientious about in terms of saying, you know what, might it be easier for me to maybe have that 4.6 and then ratchet it up. Now, in terms of when this is going to make the most sense is that hopefully you kind of get a little bit of an understanding what applications you're ready utilizing. If you take, for instance, use certain encoding applications for like taking a CD into an MP3, some of them still tend to only be maybe single-threaded or maybe two-thread support. So getting that 4.8 gigahertz is going to give you a nice bump in performance there. While other actually applications that are already taking advantage of multiple threads are going to benefit from, of course, that 4.6. So definitely something to keep in mind there. So what we're going to now go ahead and talk about a little bit is how you can actually kind of define the kind of sweet spots in terms of how to start overclocking your system. So first and foremost, generally in our experience, what we have found is that voltage is kind of one of the key parameters that kind of learning where the range quality is within your CPU. And we have found that if you have a fairly good quality CPU, one is that it will operate at a lower vid. It's generally going to be closer about to 1.375 to about 1.415 at or around 4.7 to 4.8 gigahertz. So take, for instance, this CPU is actually quite solid, and it's able to achieve operational frequency of 4.8 gigahertz at about 1.415. So that would be my first kind of initial target is let's go through the actual options that we're going to need to find that 4.8 gigahertz overclock. And once we go ahead and set those according items, we can then go ahead and see if our system actually posts successfully. So we're going to go ahead and set that to manual. We're going to go ahead and set our turbo ratio to 48. We're going to set our clock gen filter to enable. This is going to help us to extend a CPU frequency headroom by offering more capacitance in terms of the achievable power delivery. Our memory frequency, we can go ahead and manually set to 16. Now, if you do have memory where you know that the XMP profiles are 1.3 specification, you could manually define it. I do caution, though, using XMP as a profile. The main reason being is that XMP in some situations might not be too aggressive for the CPU that you're utilizing. So we do have auto rules that are kind of built into play that will automatically make adjustments to the timings. Or if you're aware, what you can also do is take advantage of some of the options that we have in our UEFI, where we can press F3, our shortcut. We could go to our SPD information, and we can go to our DIM, and we can see, oh, here's all our information for XMP. And so I know that those are kind of the key timings. And once I have those key timing information, I can go and I can manually define those parameters if I wanted to. Or just go ahead and let the board automatically dial those in. So it's kind of up to you, where if we were talking about, once again, loading XMP and redefine those values, I could have just selected that. And then turbo ratio, go ahead and set that back to 48. But once again, I do caution that with XMP, there is going to be variance. In some situations, the XMP profile that's stated either might be too conservative or it might be too aggressive. Okay. Moving past that, what we're going to go ahead and do is take a look here at our, what's referred to as our Digi power control options. Now this is kind of the heart of the actual overclocking parameter section here. A lot of these options are going to really be key at helping you define a reliable and high quality level overclock. So our first option is going to be referred to as CPU load line calibration. With load line calibration, this set of options that we have here in our multi-stage LLC lets us what's called counteract droop. When we attempt to counteract droop, essentially there's a drop in the actual voltage as the CPU gets under load. And as we overclock the system, we need to have the voltage be fairly consistent at the level that we've defined to ensure operational reliability, because we don't want that voltage to drop out and essentially then our overclock to not have the corresponding voltage as it needs to maintain stability. Now, in our testing, in most situations, the ideal option is generally going to be medium to potentially high. These are going to be the closest to being a 1-to-1 nominal value, so that if you approximately, let's say, define like 1.415, you're going to approximately get that. Now keep in mind that there's always some variance in the way that software reads voltages due to what's called the proximity to the Super I/O controller and the power plane on the motherboard. These two items, when they sync up together, help to provide the information in terms of the voltage. And sometimes, because of placement and other variables, these numbers can be fairly off. But in our internal testing, we found our numbers are pretty accurate to actually what's being provided to the CPU. If you're generally using more realistic actual usage models, so you're actually playing games and that's actually how you're going to test, medium is going to work pretty much most of the time. In some situations, if you want to be a little bit more aggressive and use higher level synthetics first initially to validate your actual overclock, high is going to be a consideration. So for right now, we're essentially just going to go ahead and go with the high option. Keep in mind that for ultra high and extreme, generally they're only advised for users that have advanced cooling configurations or potentially using exotic forms of cooling. Now, moving over to the next option, we have what's called CPU current capability, or OCP. OCP is overcurrent protection. This is a key parameter because what we need to do when we're overclocking the system is extend the OCP range. This is important because we don't want the OCP range to actually be too low. We don't want to potentially hit a ceiling when we really push up the amount of wattage that the CPU is actually consuming and putting out, and have the actual system shut off for overall safety purposes. So we're going to go ahead and choose a nominal value of 130%. This is overall going to pretty much give us enough leeway to comfortably be able to get to 4.8 and 4.9 gigahertz, and even getting close to 200 watts of power in terms of the dissipation and draw that's occurring for that CPU alone. So generally that's going to be solid. Now some people might ask, well, why do we have the red? Red means at 140% that the overall current level handling is so high that you really need to be conscientious of, one, that you're probably feeding a lot of long-term high-level voltage into the CPU. There's a lot of heat to handle, and there's just a lot of excessive variables that are being at play. So, in my recommendation is that generally, if you have to have 140% to have the system work at the defined overclock, it's probably too aggressive. But it is an option for you guys that are the ultra enthusiasts that really want to push things to the bleeding edge. And the next option that we have here is what's referred to as VCCSA load line calibration. This is an important option because for VCCSA, once we define this actual voltage, this is the kind of the voltage that lines for the memory controller. So at times, we might need to ensure that the VCCSA gets a little bit more voltage, or sometimes it's can be nominal. When we actually show which values we recommend for the voltage tables in the primary AI tweaker section, we will note that generally we don't want to exceed a 1.1 vid for the VCCSA. In most situations, that voltage level will comfortably get you 1600 and potentially up to 1866. And in some situations, even 2133 modules will run with 1.1. Now, in some situations, depending on the module as well as the actual quality of the memory controller in your CPU, you may need more VCCSA. I do not generally advise exceeding a 1.1 value, but in the event that you do, the two options you have available is either to manually define a higher value at, let's say, like 1.2 vid, which I would really not recommend exceeding. And if your XMP profile loads more than that, first try a more conservative value to see if you can run with that first. Instead of manually defining that, the other option is that you can use a little bit more of an aggressive load line option to go ahead and apply a little bit more vid and hopefully help to ensure better stability, especially as you put more heavy loads on the memory, especially at higher density configurations. For now though, because we want to keep fairly close to that 1.1 value that we're going to be recommending, we want to go with the regular option, which essentially will ensure that there's overall no overvolting that's occurring. Same thing for the VCCSA, very similar to the current capability that we noted for the CPU. It's the same thing. As you begin to go ahead and put more stress on the memory and it consumes more current and more power, we want to go ahead and open this up. In most situations, most users aren't going to readily use a lot of the memory, so it's not going to probably run into an issue. Once again, if you use those really high-level synthetics, this is going to be a key item to help ensure high-level stability. So we're going to go ahead and go with 120% for this. Now, you probably saw that we have these two boot up voltages. In some situations, these can potentially be key at helping you define additional voltages that might be required during what's called the post state and then the boot stage of your system, but that won't actually be required for the actual normal operation of the system. So as an example, potentially maybe the CPU might require 1.450 to boot fully, but it's actually normal default vid that might be required to operate might be as actually small as 1.415. So that is something that you kind of can play around with, but in most situations, generally it won't be required, but it's a nice option to have there. For CPU voltage frequency, this actually helps to adjust our VRM switching frequency. In most situations, I recommend that you leave this to an actual auto parameter. In some situations at very high level loads, we have found that you can potentially sometimes improve stability by increasing this, but keep in mind that the VRM switching frequency as it increases will produce more heat, so we really want to keep the actual VRM assembly cool through adequate airflow. Through Spectrum, we're not going to worry about that option right now. It's more targeted at helping to ensure better reliability and overall efficiency when we're running closer to a nominal standard stock operating parameter. For CPU power duty control, this is an ASUS exclusive design option that we have for our VRM. Essentially, we have the ability to go ahead and control the actual what's referred to loading policy for our actual phase array. So if we actually look at our motherboard, the motherboard actually has these chokes, which when combined with the MOSFET in the driver create a phase. And what our actual duty control does is when set to T-probe, it will monitor the temperature of these phases. And as we're monitoring the temperature per phase, we can help to distribute the load across the VRM so that we minimize a potential hot spottiness, giving us overall better temperature efficiency and quality power delivery at the same time. Now this does potentially artificially cap the maximum power delivery that's being supplied. So the other option that we can go ahead and go to is extreme, which will force these, instead of being based on temperature loading, to be based off of current loading. So helping us to achieve the maximum current delivery. Of course, that will also produce more heat as well. Generally, extreme value setting is only advised when you're considering using a voltage and corresponding frequency that aligns with 4.8 plus. So in most situations, including at 4.8, you're generally going to be able to do the job with T-probe. So we're going to go ahead and keep that as our actual option there. For CPU power phase control, this option is really focused actually at power consumption, and it's going to be more critical for idle and moderate level loads. When your system actually goes under full load, it actually will generally use the entire VRM phase array to ensure quality power delivery. But what we can do is if we keep things like C states on, like C1E, C3, C6, C7, and the CPU is actually dropping down, then we can actually try to help to improve the power efficiency because we can control the actual phase management at those points. So when we define these options, things like standard is generally going to use somewhere between about 1 to 4 phase. Optimizer is going to use 1, 2, 4, 6, 8, and onward up until the maximum phase count. And extreme, regardless of whether you're at idle, at moderate loads, or high loads, is always running the VRM at full utilization. This helps to ensure the most consistent high level power delivery, but it will also produce the most heat. For the VRM, because heat is actually not our friend, it brings down the operational efficiency. Try to keep the VRM as cool as possible to really help ensure the best quality power delivery. For our purposes, generally optimize is going to be fine up to and around 4.6 to 4.8. After that, once again, just like T-probe, you may need to consider extreme. Now we've got a couple last options here, and these are going to be very similar to the other options that we defined. So for current capability, we're going to go ahead and set that to 120%. For the phase control, we're going to go ahead and set that to optimize, and same thing for the corresponding opposing channels. And those current capability and phase controls are very much similar in terms of what they do, but relative to the DRAM, just as what we defined actually for the CPU VRM options. So we're going to go ahead and move back out now that we've gone ahead and defined those parameters. For CPU performance settings, we're going to leave actually all these nominally to actually auto because our boards have very strong auto rules where you don't need to go ahead and define these actual operational limits. Now in terms of our vCore, we have two options. We have what's referred to as a manual vid and an offset vid. Now this is critical. With an offset vid, it's actually a much more efficient, reliable mechanism in giving voltage to your CPU. Because as the CPU multiplier increases, and what's referred to as the vid, the voltage table actually will increase nominally as the multiplier increases. So what we can do is we can just apply a small voltage offset at each one of those steps as you go up, helping to provide quality voltage power delivery for that corresponding frequency. Now the one disadvantage is sometimes it can be hard to figure out what offset table you need. And most recommendations, depending on the level that you're looking for between about 4.6 to about 4.8, I generally will advise a rated operation of 0.165 to 0.200. This will generally give you about the voltage level that you need for those frequencies. Potentially a little bit more might be required depending on the quality of your CPU. Now the main benefit of an offset is that if you have speed step and C states enabled, as the CPU frequency goes down, your voltage is also going to go down. So you're not consistently always giving a high level of voltage. Now with the higher clock speeds, like generally 4.8 and above, in some situations, the fluctuations that are going to occur can potentially cause the CPU to drop out. So what we might need to do is force a much more consistent manual vid. In that situation, which is what we're going to go ahead and define right now, keep in mind that even with C states enabled, you'll get a little bit drop in power consumption, but you are going to consistently be giving your CPU the same voltage at idle that you're also giving it at full load. So it's not necessarily the most efficient, and it's also going to actually produce the most heat because you're getting much more vid being supplied to the CPU even at idle than you would be if you were using an offset. So remember, we talked about trying to set up values to go ahead and see what the quality of our CPU was, and that's going to be 1.410. Generally, if your CPU can hit this manual vid option of 1.410 and a 48 multiplier, you've got actually a pretty strong CPU. And most of them will be able to hold that 1600 memory divider. Generally, when you exceed that though, things could become a lot more tricky in terms of knowing whether it's the memory divider frequency or it's the actual multiplier frequency that's limiting you. So try to make sure that you do one or the other and not necessarily both in terms of trying to pursue really high clock frequencies for both the CPU and the DRAM. But you want to try to focus on one or the other, or do them incrementally to see where the ranges of operation are. So we've got 1.410 set. For our VCCSA voltage, very similar, we have that offset and that manual policy that we discussed. For the VCCSA, my recommendation is just pretty much to be consistent and set it to a manual level of operation, and we're just going to go with 1.10. That's going to be my recommendation pretty much across the board at whatever configuration you're running, if you're running 1600 and above. Now, like I noted before, at some higher DRAM dividers and potentially more aggressive memory configurations, you might need more than this, but my active recommendation is generally not to exceed this value unless it's absolutely required for the stability of your DRAM configuration. For our DRAM voltage, we can see that XMP has already gone ahead and defined those for us. CPU PLL, this is actually a key voltage that sometimes at higher clock frequencies, you might need to actually increase this to help minimize clock jitter. This can help to strengthen the actual CPU frequency parameters and go ahead and potentially give you an improved level overclock. In most situations though, the default value of 1.80 is going to be adequate at ensuring reliability for 4.8 gigahertz. So we're not going to adjust this value at this point. For VTT, generally we want to keep this kind of linked in with the VCCSA as they help each other out. So we're going to keep this pretty much at a match parameter value. And once again, the recommendation would generally not be to exceed 1.10. For PCH voltages, those actually are for our platform controller hub for our serial ATA operation. In our internal testing, we found no reason at all to change those parameters. So we're just going to go ahead and keep those at default operation. So from the rest there, we have a lot of different options that we see available for DRAM reference voltages. These are really for the die-hard enthusiasts that if you want more information on what you can do with these and what they're applicable for, make sure to head over to our ROG forums. But we're not going to be touching on these because for our overclocking demonstration, we're not going to need to generally modify those parameters. Now, before we step out of this overall primary area and just touch on the last couple of options that we have at defining our manual OC, it's very important that you remember one other item. And this is referred to as memory training, when your system is actually going through a post-cycle. The post-cycle actually will get information that's being sent from the IMC, so the memory controller and the CPU, and exchanging it back and forth between the UEFI and then also initializing the DRAM. And some more aggressively configured configurations at higher DRAM dividers and also with higher density modules, memory training differences can make or break a potential overclock. With the same exact defined settings from one reboot to the next, sometimes there might be enough of a value of change that this can change your overclock. Now, there are some special slew options that we have available here that you can adjust to sometimes give you better normalized patterns that won't always accept the new memory training that occurs during reboot stages. In most situations, you generally should be okay, and this is something that you should not be worrying about. But should you run a situation that overall it looks like everything's right, but you tend to run more into an issue when you're pushing with the memory, or sometimes things seem a little bit inconsistent, once again, you can also head over to the ASUS ROG forums, where we'll have some more information regarding those specific advanced options. So moving over from there, we've got CPU configuration. and we're going to actually go ahead and disable Intel Thermal Adaptive Monitor. Now this does not disable the ability of the CPU to still have what's called TCC control, which means that once the CPU gets approximately between 88 to 91 C internally in terms of its recognized temperature, that it will actually either generally shut down or throttle out. So this is just to minimize the likelihood from the board registering any temperatures and artificially bringing our CPU frequency down. As we noted before, if you're generally running realistic applications at the voltage levels defined, you would never even hit the thermal monitor parameters, but just as a precaution and to ensure high level overclocking performance, we're going to want to disable this. Now, relative values like execute bit, disable bit, and virtualization technology, we're going to go ahead and leave those enabled because we haven't generally found that they affect overclocking performance. Now, as we go into power management, this area is kind of key. There's two ways to go about it. If you really want to be power efficient about overclock, hopefully you're going to utilize an offset voltage. And if you do that, you want to keep all your parameters like C1E, C3, C6, and C7 enabled. This will help to ensure that the CPU actually downclocks to the lowest power stages when it's under an idle or moderate state. So this gives you a lot of flexibility. If you're one of the people that always want to run full bore out consistently, then you can disable these values like C1E, C3, C6, and C7. Keep in mind though, that will continuously run the frequency of your CPU locked in at a 4.8 gigahertz value, as opposed to dropping from 4.8 and essentially going down to a baseline of 1.2 gigahertz. This is an important consideration to make because it can affect potentially the long lifespan of the actual CPU. So just something to keep in mind. For us right now, we are going to go ahead and actually keep these disabled. Now keep in mind that if you force these values, sometimes the CPU frequency can be more consistently held, of course, at that higher value. So sometimes a higher level of voltage might be required when this occurs. Now, another interesting consideration that we've seen is that with a very aggressive overclocking, we have found that C-states can potentially be an effector at cold post effectiveness at coming back from a high level overclock. In some situations, these C-states can induce issues with the system coming from a cold post, even at completely validated and stable settings. So if you run into a potential issue where you quantify everything runs through well, your quantified results are stable and solid, but after a cold post, potentially the system does not complete a boot, or it's not stable, reposting and rebooting through, disable these C-state values, and generally that should allow you to get back to a normal operating parameter. Now this could also be a sign though that the overclock that you have defined is necessarily held by a weaker multiplier, and at the end of the day you might want to consider maybe dropping one step so that you can also maintain those C-state values. That's a consideration for yours to make. So at this point we're going to go ahead and actually leave these to enabled. And for the most part, we pretty much almost looked at all the key items that we want to define within our UEFI. We've got one other option here in terms of the monitor that we're going to go towards, and that's going to be anti-surge support. For anti-surge support, we're actually going to disable it. The main reason why we're going to disable it is that for our anti-surge monitor, it works with the Super I/O controller, and there's no way for a Super I/O controller to know the difference between a potential surge or spike or sag, which has a really high level of wattage and current, as opposed to the very high level wattage and current that you're going to have when you're defining a very high level overclock. When this setting is left on, potentially when you get to these really high levels, 180, 190, 200 watts, the system actually could artificially shut down to protect itself because the anti-surge has been enabled. If you've got a very good quality CPU and you can run lower voltages, you could probably still keep this option on. But for aggressive overclocks, such as the one that we're trying to define, we're also going to leave this value actually at disabled. Okay, so from here, we've pretty much got kind of all the key parameters that we want dialed in. So we've got 4.8, 1600, we've got pretty much all the accorded values that we want. At this point, pretty much what I would advise is make a little bit of a note here in terms of what you have running. If you want, also go ahead and take advantage of our OC profile option. We could define in, this is 4.8 gigahertz. We're going to save this so that we know that we have this option to profile 1. And pretty much from here, we're going to be good to go. So this is going to be the end of the initial overview for the UEFI level of overclocking. So at this point, what we're going to go ahead and now do is press F10 and see if the system actually goes ahead and successfully posts and also completes a boot. So at this point, the system's gone ahead and now registered these entire new set of settings. We'll go ahead and reboot. It will now repost with all the new defined parameters, which essentially is our 4.8 gigahertz, 1600 megahertz on the memory, the voltage table at 1.410, our VCC, SA, and VTT at 1.1, and the rest of the parameters that we've gone ahead and defined. And as we previously noted, generally if your CPU can boot in at these values that we've defined, you've got a pretty solid CPU. Now, just because it can go ahead and post and boot doesn't mean that the CPU will actually be stable at these values. There is still a definite possibility that while it's able to boot in at these values, that the overall stability, once it's actually stressed, still might be compromised, and you still actually might need more voltage. And that's where things can definitely get interesting, where instead of having to go manually back and forth into the actual UEFI, we can go ahead and actually make adjustments real time within the operating system within AI Suite 2, where we can add more voltage as we're running an actual real-time stress test. So as we can see right here, we're getting to the Windows loading process. Now generally, as this is the initial part of the OS, the turbo multiplier is being kicked in because all the actual values are being realized in terms of turbo now being executed, because we're essentially in an operating system environment. It would usually fail to enter in here. And if it just got locked there, then generally it would be an indicator that the voltage is generally too weak for the corresponding frequency. So if, let's say, I had a weaker CPU at 4.8, hit that 1.410, and it still was not completing a boot, I would have to go back, and I would probably want to try to adjust in increments of, I'd say, approximately 0.15 to 0.25. So we would go up from maybe 1.410 to maybe 1.4 to 30 as an option, and see if then the system was able to successfully post and boot. So we can see here, we've actually gone ahead and successfully completed 4.8 gigahertz. We're going to go ahead and check the frequency and see how things have turned out. So we're personally using ASUS. We've worked extensively with them in terms of sending feedback reports to them based on CPU architecture for the latest Sandy Bridge E CPUs, the X79 chipset, and specifically our motherboards. We prefer this over CPU-Z because as CPU-Z is a great utility, it has more of an issue in terms of really being updated and also validated for latest architectural designs. So as we can see here, we've got 4.8 gigahertz, and we can actually see that also with our C1E and C-step values, it's actually bringing the actual CPU down because it's under idle to 1.2 gigahertz. But we can see it bumps up back and forth there. So an example, let's say if we were going to go ahead and run a quick benchmark on the system, our CPU is actually going to go ahead and run into the maximum load multiplier, which is going to be that 4.8 gigahertz frequency. So this gives you an overall idea in terms of how to define your UEFI BIOS to go ahead and begin the process of overclocking. This is going to be the end of the first part of our advanced overclocking tutorial guide. In our second part of our advanced overclocking guide, we're going to be looking at things such as power draw, how to effectively look at applications, how they consume power, how voltage is important to those parameters, how to factor in considerations for temperatures, and a lot of other variables to keep in mind. So as always, if you guys have any questions, comments, feedback, make sure to leave them here on the YouTube page, or make sure to check us out at asusrog.com/forums, where you can find me, ASUS Illuminati, or any of one of our number ROG team members, where we have more information relative to our ASUS X79 boards and how to maximize your overclocking potential. As always, thanks for watching, guys.